Welcome everyone to this video, further discussing reaction mechanisms and getting rates and rate laws from them. So let's consider a mechanism here, 2A going to B and B plus D going to P, right? Right. So given this reaction mechanism, I can ask all sorts of questions, right? I can ask things about what is that rate of change of concentration of B, right? And from there, we can say, okay, well, B here, right, in the first reaction, B is being produced, right? So the change in concentration of B, right, is going to be related with K1A squared, right? And that's because, right, so in the first reaction, right, what we have is we have the rate law is V1 equals K1A squared, right? Because again, the rate law for that first reaction is just the concentration of the reactants, right, multiplied together times the rate constant, okay? Right, and we know, right, for that first reaction that the change in concentration of B with respect to change in time is just equal to V1 for that first reaction, right? Because again, it's a product, right? So the rate of formation of that product is related with the rate law, right? Now I would divide by the stoichiometric coefficient, but the stoichiometric coefficient here is 1, so it doesn't really change anything, right? Okay, and so that's what we have for the first reaction, okay? Now for the second reaction, right, B also, its concentration being changed by that second reaction. It's appearing in both reactions, so both reactions affect the concentration of B. And B here, right, is now a reactant, right? And again, the rate law for that second reaction, V2, is equal to K2 concentration of B times concentration of D, right? So, right, and so for that second reaction, that's what we get, right? And so again, that rate is related, right? V2 is related with the rate of change of B. Now here, B is a reactant, so there's a minus sign that appears, right? That minus dB dt equals V2, right? For the second reaction, okay? So I got that minus sign, right? Because the concentration of B is decreasing for the second reaction, right? Where this thing here just equals V2, right? Or minus V2, I guess. Okay, so the overall change in concentration of B is just the sum of these two things, right? And I have this, right, final form, okay, for the overall change in concentration of B, okay? Right. Now, if we were to do the same thing for A, okay, right, we need to take into the fact, right, in that first reaction, right, I have, again, this is the rate for the first reaction, okay? But the change in concentration of A with respect to time minus 1 over 2 equals V1, right? So for the first reaction, right, dA dt, right, solving for that equals minus 2V1, right? And I can plug in V1 from up there, right? But notice that I have this coefficient of 2 here that appears because of this stoichiometric coefficient of 2 that appears in front of A, right? And that only appears, that 2 only appears when I'm talking about the change of concentration of A, right? That 2 does not appear when I'm talking about the change of concentration of B, because change of concentration of B only depends on the stoichiometric coefficient of B, okay? Now that 2 always appears in the exponent, okay? So you just got to keep in mind sometimes these stoichiometric coefficients, where they appear, where they don't appear, right? And it's good. We'll do lots of examples of this, right? And it's good to just be very slow and meticulous to make sure you're writing out the rate laws and their change in concentrations, and you know exactly right. Okay. So let's consider some sort of elementary reaction that has an equilibrium established, right? So here I have an equilibrium between 2A and B that's occurring with a forward rate constant K1 and a reverse rate constant K minus 1, okay? So going through kind of the steps talked about before, right, you can write out the changes in concentrations A, B, D, and P given by these formulas, okay? Right? Again, we can, for example, let's just do A in particular, right? A only appears in that first reaction, right? But the first reaction has a forward reaction and a reverse reaction, right? For the forward reaction, the change in concentration of A with respect to time, right, is -1/2 equals V1, right? And the reverse reaction, we have 1/2 dA dt equals V2, right? Or sorry, not V2, V minus 1, right? Where again, V1 is the rate law, okay, for the forward reaction, which is just K1A squared, okay, right? This is just K1A squared, right? And then V minus 1 here, right, is the reverse reaction, okay? And that is going to equal K minus 1, right, B. Okay? And so then that's how we get the final equation here, minus 2K1A plus 2K1B, right? Because I have to then move this stuff onto the other side. That's where the factor of 2 and the factor of -1 comes from. Okay? Right. So if we have this reaction mechanism where some reaction's in equilibrium, right? First thing to note is that if this is an equilibrium, right, if the equilibrium is established, that does not mean K1 equals K minus 1, right? That is not true. What it means is that the forward rate is equal to the reverse rate, right? The forward rate for this reaction is K1A squared. I forgot a 2 here. The reverse rate is K minus 1B, right? And so those two things equal each other, and so you get this relationship here, okay? Which if you look at that, okay, concentration of B over the concentration of A squared equals your equilibrium constant, capital K, right? And so, right, what that means is that K1 does not equal K minus 1, but the ratio of K1 over K minus 1 equals your equilibrium constant K, right? Right, so those, so the ratio of those rate constants is related to the equilibrium constant itself, okay? Right, but they are not equal to each other even when equilibrium is established, right? Equilibrium established, it's that reverse rate and forward rate that are equal, not the equilibrium, or not the rate constant. Okay. So here we're going to finish up this video with one kind of example. We're going to solve for what the concentration is for this very simple mechanism. The concentration of A, concentration of I, and concentration of P is a function of time. Okay, and why we're doing this is to kind of show you for a very simple mechanism here, just 2 steps, 1 intermediate, okay, 1 reactant, 1 product, how complicated solving for these concentrations as a function of time can be. Okay, and in general, what we do in practice is often use certain approximations to simplify a lot of this stuff. And we'll see what these approximations are in future videos. Okay, but for here, we're going to go through and do kind of the effort to solve for things exactly. Okay, right? So I have this mechanism. I can write out these rate of change equations, right? Change of concentration of A as a function of time, change of concentration of the intermediate as a function of time, and then change of concentration of P as a function of time, right? And these are all right, very simple equations here, right? Okay, and A here is a reactant, so you get that minus sign. Okay, P is a product, so it's just dependent upon the rate of that second reaction, right? And then I appears in both reactions, and it's getting formed in the first reaction and consumed in the second, so you got the plus and the minus there, right? So we have these equations. These are all differential equations, right? Well, we can first solve the differential equation for A, right? That's just a first order rate law expression. So we get our integrated rate law for first order, okay? So concentration of A is equal to concentration of A naught, e to the minus KAT, okay? Right, now if I plug that in to the differential equation for I get this equation here, okay? Right, which is just an equation that depends on the concentration of I in time, right? So it's also a differential equation, okay? But this isn't as simple of a differential equation to solve, okay? right? We won't go through how to solve this differential equation, okay? But we'll just kind of present here that the solution to this differential equation is as follows. Concentration of I is equal to the initial concentration of A times Ka divided by Kb minus Ka, okay? Where again, like Ka is equal to kind of K1, right, the rate constant for the first reaction, Kb is equal to K2, the rate constant for that second reaction, right? And then e to the minus Ka T minus e to the minus Kb T. Okay? So this is the differential equation, this is the solution to this differential equation that we had found above. Okay? Finally, we can get the concentration of P. Now we could try to do that by solving and integrating, doing some stuff like that, or we can do it in sort of a simpler mathematical way, but you know, in just relating the fact, right, that based off the stoichiometric coefficients, right, the concentration of A plus the concentration of I plus the concentration of P always has to equal the initial concentration of A. And I solved for what this is, right, the concentration of A and the concentration of I as a function of time. So I can just plug those in, okay? Right, for the concentration of A, I have e to the minus Kat, right? And what so how I got this equation right is I put the concentration of A naught minus concentration of I minus concentration of A, right? That equals concentration of P. Okay. And so, right, we have e to the minus Kat, right? That is from the concentration of A, right? There's a factor of A naught that gets pulled out in front, right? I have, you know, this A naught multiplied by 1 here gives me that A naught term up here, right? So that's where this comes from, right? And then the intermediate gives me that complicated expression there, right? And you can simplify this thing down, find common denominators if you want to, and things like that, and get this expression here for the concentration of P. Okay? So this is our final expression for what the concentration of P is as a function of time. Okay? Right, and so now, right, we finally have what the concentration of A is, concentration of I, and concentration of P is a function of time. And I can plot these things, right? Given whatever value Ka is, Kb, I can plot these things, right? And I can look at, you know, the concentration of A, and what does that look like here, right? The intermediate, how it grows and then decays, right? Get the concentration of that I, right? Concentration of P, right, is, right, what does the product look like as a function of time, right? And so we have these different right, plots, right, and I can mess around and change what Ka is, what Kb is, and look at what these things look like, right? And so this gives us a nice, you know, example of what these concentrations look like and how complicated it can be to solve for these concentrations, right? Even for a very simple mechanism, right? And so in the next set of videos, right, we'll be going over different approximations that we can make. We'll kind of compare those approximations to these exact answers for the simple mechanism, right, in order to kind of say when can we make these approximations, when are they valid, right, and see how they help simplify some of the math and some of the things that we're doing. Okay.